Dear students, Physics Practical ਦੀ audio visual series ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਅਸੀਂ ਦੋ experiments ਕਰਾਂਗੇ ਜਿਹੜੇ ਹਨ to study the current voltage characteristic curves of a PN junction diode in forward bias and reverse bias ਅਤੇ to draw the characteristic curves of a Zener diode and to determine its reverse breakdown voltage. A PN junction is formed by joining P-type and N-type semiconductors together in very close contact. The term junction refers to the boundary interface where the two regions of the semiconductor meet. If they were constructed of two separate pieces, this would introduce a grain boundary. So, PN junctions are created in a single crystal of a semiconductor by doping. For example, by ion implantation, diffusion of dopants, or by growing a layer of crystal doped with one type of dopant on top of a layer of a crystal doped with another type of dopant. PN junctions are elementary building blocks of almost all semiconductor electronic devices such as diodes, transistors, solar cells, LEDs and integrated circuits. They are the active sites where the electronic action of the device takes place. The discovery of the PN junction is usually attributed to American physicist Russell Ohl of Bell Laboratories. Today, as our first experiment, we are going to study the current voltage characteristics for a PN junction diode, both in forward bias as well as reverse bias. So, आओ ਹੁਣ ਅਸੀਂ PN junction diode ਦੇ IV characteristics curves study करिए. The theory behind this experiment says,
इस एक्सपेरिमेंट दा ऑब्जेक्टिव है to study the IV characteristic curves of a PN junction diode in forward bias and reverse bias. The requirements of the apparatus are as these: a PN junction diode, a 3-volt battery, a high resistance rheostat, 0 to 3 volt voltmeter, 1 milliammeter, 1-way key, and some connecting wires.
According to the theory of this experiment, a PN junction is a semiconductor device. This is generally made by putting a P-type semiconductor in contact with a N-type semiconductor. This results into one-piece device, which is commonly called as a junction diode. A junction diode can be biased in two different ways, namely forward biasing and reverse biasing. In forward biasing, the P-type of crystal is connected to the positive of the bias battery and N-type to the negative of the bias battery. As the forward bias is increased, the current also increases. The current increases slowly in the beginning and then goes up sharply. The forward current flows only if the initial forward voltage is greater than a certain minimum voltage, which is known by the name knee voltage. On the other hand, a PN junction is said to be in reverse bias if the p-type crystal is connected to the negative terminal and n-type to the positive terminal of the bias battery. Now, a very small current, that is of the order of microamperes, flows due to minority carriers. This current is called as saturation current because it is found to be independent of the reverse bias. At a certain reverse voltage, the current suddenly increases due to the breaking of the covalent bonds. This reverse voltage is called the Zener breakdown voltage. ਇਸ ਦੀ ਥਿਊਰੀ ਤੋਂ ਬਾਅਦ ਚਲੋ ਹੁਣ ਇਸ ਐਕਸਪੈਰੀਮੈਂਟ ਦਾ ਪ੍ਰੋਸੀਜਰ ਵੀ ਸਿੱਖ ਲਈਏ।
ਇਸ ਐਕਸਪੈਰੀਮੈਂਟ ਦਾ ਪ੍ਰੋਸੀਜਰ ਇਸ ਤਰ੍ਹਾਂ ਹੈ। ਪਹਿਲਾਂ ਅਸੀਂ ਫਾਰਵਰਡ ਕੈਰੈਕਟਰਿਸਟਿਕਸ ਲਈ ਕੰਮ ਕਰਾਂਗੇ। Make the connections according to this circuit diagram. Keep the moving contact of the rheostat to the minimum and insert the key K. Voltmeter and milliammeter will show a 0 reading at this time. Move the contact towards the positive terminal of the battery to apply the forward bias voltage. Vf is equal to 0.1 volt. The current remains 0. Next, increase the forward bias voltage to 0.3 volts in steps. The current will still remain 0. This is due to the junction potential barrier of 0.3 volts. Further, increase Vf to 0.4 volts and record the current. Then increase Vf in steps of 0.2 volt and note the corresponding current and voltmeter readings. At Vf equal to 2.4 volts, the current increases suddenly. This represents the forward breakdown stage. Draw a graph between V and I, taking V along the x-axis and I along the y-axis. The graph will be as shown here. ਆਓ ਹੁਣ reverse biasing ਲਈ ਵੀ circuit diagram ਵੇਖੀਏ. The circuit is to be modified for reverse biasing. The modified circuit looks like this one. Remember, we will be plotting current voltage characteristics using this modified circuit shown here. The voltmeter, as before, is connected across the PN junction. The milliammeter is replaced by microammeter as shown. The procedure for reverse biasing is just the same as for forward bias. The microammeter readings should be noted, corresponding to different voltmeter readings. Then, a graph between V and I is plotted by taking V along x-axis and I along y-axis. The graph obtained is as you can see here. It is now time to list down the precautions set for this experiment. Measuring instruments must be of proper range. Make all connections neat, clean and tight. Key should be used in circuit and opened when the circuit is not in use. Avoid applying forward bias voltage beyond breakdown. There are certain sources of error possible, which have to be taken care of. The connections may not be tight. The junction diode may be faulty.
Dear students, we have set this class to learn to perform two experiments related to diodes only. So, let's now take over with the second experiment lined up for today. In this experiment, we will draw the characteristic curves of a Zener diode and determine its reverse breakdown voltage. I hope you distinctly understand a Zener diode. It is a special purpose semiconductor diode named after its inventor C. Zener. It is designed to operate under reverse bias in the breakdown region and is commonly used as a voltage regulator. The symbol for Zener diode is made like this. Zener diode is made up by heavily doping both P and N sides of the junction. The depletion region formed is very thin because of this reason. It is of the order of less than 10 raised to the power minus 6 meter. The electric field of the junction is extremely high, of the order of 5 into 10 raised to the power 6 volt per meter, even for a small reverse bias voltage of about 5 volts. Here are shown the current voltage characteristics of a Zener diode. It is seen that when the applied reverse bias voltage V reaches the breakdown voltage Vz of the Zener diode, there is a large change in the current. Note that after the breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. Or it can be said that Zener voltage remains constant, even though current through it varies over a wide range. This property of the Zener diode is used for regulating and rendering constant supply voltages. Let us now understand how reverse current suddenly increases at the breakdown voltage. We know that reverse current is due to the flow of minority carriers, that is, electrons from P to N and holes from N to P. As the reverse bias voltage is increased, the electric field at the junction becomes significant. When the reverse bias voltage V is equal to Vz. Then the electric field strength is high enough to pull valency electrons from the host atoms on the p side, which are accelerated to the n side. These electrons account for high current observed at the breakdown. The emission of electrons from the host atoms due to the high electric field is known as internal field emission or field ionization. The electric field required for field ionization is of the order of 10 raised to the power 6 volt per meter. We know that when the AC input voltage of a rectifier fluctuates, its rectified output also fluctuates. To get a constant DC voltage from the DC unregulated output of a rectifier, we use a Zener diode. And now, let us learn to study the characteristic curves of a Zener diode experimentally.
The objective of the experiment is to draw the characteristic curves of a Zener diode and to determine its reverse breakdown voltage. The apparatus required for the experiment is a Zener diode with reverse breakdown voltage of 6 volt, a 10 volt battery, a rheostat, 2 voltmeters of range 0 to 10 volts, 1 microammeter with range 0 to 100 microampere, 1 20 ohm resistance, a one-way key, a few connecting wires. Let's now understand the theory that works for this experiment. Zener diode is a semiconductor diode in which the N-type and P-type sections are heavily doped. This heavy doping results in a low value of reverse breakdown voltage. Zener diode is always operated in the reverse bias. It works as a normal diode in the forward bias. The reverse breakdown voltage of Zener diode is called Zener voltage, denoted by Vz. The reverse current that results after the breakdown is called Zener current. The circuit diagram is as you can see here. Let me also tell you the meanings of the abbreviations used in this circuit diagram. Vi equal to input voltage. Vo equal to output voltage. Ri equal to input resistance. II equal to input current. Iz equal to Zener diode current. IL equal to load current. IL equal to II minus Iz. VO equal to Vi minus II into Ri, or VO equal to RL into IL. Initially, as input voltage Vi increases, II, input current, as well as output voltage VO both increase. At breakdown, increase of input voltage Vi increases, input current II by a large amount, so that output voltage VO is equal to Vi minus II into Ri becomes constant. It is for this reason that it is used as a voltage regulator. This constant value of VO, which is nothing but the reverse breakdown voltage, is called the Zener voltage. Then, to start the procedure, we will begin with making the connections according to scheme of connections, while making sure that Zener diode is reverse biased. Bring the moving contact of rheostat to the minimum and insert the key K. Voltmeter and ammeter will read 0 at this moment. Move the contact a little towards positive end to apply some reverse bias voltage Vi. Milliammeter reading remains 0. As input voltage Vi is further increased, input current II starts increasing, and output voltage VO becomes less than input voltage Vi. Note the values of input voltage Vi, output voltage VO, and input current II. Keep increasing input voltage Vi in small steps of 0.5 volts. Note the corresponding values of input current II and output voltage VO. At one stage, as input voltage Vi is increased, input current II increases by a large amount and output voltage VO does not increase. This is reverse breakdown situation. As input voltage Vi is increased further, input current II will increase, keeping output voltage VO constant. Record your observation in the observation table. Draw graph of output voltage VO along y-axis and input voltage Vi along x-axis. The graph will be somewhat like this. Draw graph of input current along y-axis and input voltage along x-axis. The graph will be as shown in figure here. Then record in your notebook under the heading Observations. Least count of voltmeter V1 equal to 0.1 volt. Least count of voltmeter V2 equal to 0.1 volt. Least count of microammeter equal to 1 microampere. Finally, after recording your observations, the observation table should appear like this. Give a careful look at the observations. Then, this is how we present the result. The reverse breakdown voltage of Zener diode is equal to 6.0 volts. No experiment can be a complete success without following certain precautions. For this experiment, the desired precautions are: use voltmeter and microammeter of suitable range. Connect the Zener diode PN junction in reverse bias. The key should be kept open when the circuit is not in use. There are some sources of error that can creep in and hamper the results. Voltmeter and ammeter may have a zero error. All the connections may not be tight. Error creeps in the readings of microammeter and voltmeter.
As you know, students, practicals are always associated with oral questions known as viva. I will now put some questions that can be presented in viva for these experiments. The first of the questions is: what do you understand by reverse breakdown current? What is its cause? The answer says, at certain state of increased reverse bias voltage, the reverse current increases suddenly. This is called reverse breakdown current. It is due to the rupture of covalent bonds. My next question is: how is a common PN junction diode different from Zener diode? The answer is: a Zener diode is comparatively heavily doped and the breakdown voltage is smaller and sharper. A Zener diode can be used as a voltage regulator. It is always reverse biased. The next question is: does the width of the potential barrier in a PN junction depend upon biasing? The answer says yes, it does. The barrier width increases on reverse biasing and decreases on forward biasing. Look at another question. At Zener breakdown, why does the current in PN junction in reverse bias increase suddenly? The answer: as the reverse bias is increased, a small current due to minority carriers flows in the circuit. On further increasing the reverse bias, the covalent bonds break due to the large increase in the electric field. The next question: how does the Zener diode act as a voltage regulator? The answer: the output voltage remains constant and is always equal to Zener voltage, whatever be the input voltage. The excess voltage, if any, is dropped across a series resistor. Here is another question. Why is the depletion region so called? The answer is, this is so because there are no charge carriers present here. The electron and holes have been lost by their recombination. आस है कि ਤੁਸੀਂ ਅੱਜ ਦੱਸੇ ਗਏ ਦੋਨੋਂ ਐਕਸਪੈਰੀਮੈਂਟਸ ਦਾ ਪੂਰਾ ਲਾਭ ਲਿਆ ਹੋਣਾ ਹੈ ਅਤੇ ਨਾਲ ਹੀ ਇਹਨਾਂ ਨੂੰ ਇੰਜੋਏ ਵੀ ਕੀਤਾ ਹੋਣਾ ਹੈ। ਅੱਜ ਦੇ ਲੈਸਨ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਹੋਰ ਨਵੇਂ ਟੌਪਿਕਸ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਤਦ ਤੱਕ ਗੁੱਡ ਬਾਏ ਐਂਡ ਆਲ ਦ ਬੈਸਟ।